Welcome to the Explainer. Today, we're diving into something pretty radical, a new framework that doesn't just try to explain quantum mechanics, it might actually give us the instruction manual to control it. All right, so let's just jump right in. We've all heard it a million times, right? The quantum world is bizarre. It's unpredictable. It's just plain weird. But what if all that strangeness isn't random at all? What if it's actually following a very specific, very predictable set of rules? Like an algorithm that we're only just now starting to figure out how to read. So, to get a handle on this whole blueprint, you've got to start with one simple, totally non-negotiable rule. This one thing governs everything else that follows. And this is it. This isn't just some quirky little feature of the universe. No, it's an absolute algorithmic necessity. I mean, think about it like a computer program. A computer has to actually run the calculation before it can spit out the final result, right? Well, in the quantum world, the wave is that calculation, and the particle? That's the result. One has to happen before the other. Period. Okay, so what does this whole wave then particle sequence actually mean in practice? It helps to stop thinking of it as some kind of magical transformation and start seeing it for what it is: two distinct, totally logical phases of one single process. And this really breaks it down beautifully. Step one is the wave. This is where the system is exploring every single possible path and outcome, all at the same time. It's the calculation running in the background. And only when that's totally finished does it snap into step two, the particle. That's the one single concrete result that becomes real.
Yeah, let's go back to that computer analogy. Your laptop can't be both processing a video and displaying the final frame at the exact same instant. It's just not possible. It's the exact same logic here. The wave is the process, the particle is the product. One state has to come before the other.
Okay, but wait a minute. If it's all just a calculation, that leads to a huge, huge question. Can we mess with it? Can we influence the outcome? Well, according to this framework, the answer is a resounding yes. It suggests there's a hidden variable, sort of like a control knob for reality itself, and it's called omega. So this omega, or coherence coupling, this is our control knob. You can think of it as a measure of attraction. During that wave phase, when all the possibilities are being calculated, omega is the thing that determines which path the system is most drawn to. It's what stacks the deck for one particular outcome. So the big question is, how do we actually turn this knob? Well, what better place to test it out than the classic, the famous double slit experiment? This is where the rubber really meets the road. All right, so in a standard everyday double slit setup, the omega value for both slits is pretty much identical. The attraction is equal. So naturally, during that calculation phase, the system explores both paths equally. And what do? You get that classic, beautiful wave interference pattern on the screen. But what happens if we start turning the knob? What if we say, increase the coherence right near the left slit, really cranking up its omega value? All of a sudden, the whole calculation gets biased. The system is now way more attracted to that left slit. And this framework predicts that the particle will be forced to choose that path. We're not just observing anymore. We're directing traffic. And here's the kicker. This isn't some abstract thought experiment. We can actually do this. We can engineer it. You could place a coherent light source near one path, or physically change the shape of one of the slits, or even apply an electromagnetic field. All of these things would change the local omega values. We can literally steer the outcome. This isn't philosophy, folks. It's an engineering diagram. Okay, deep breath, because this is where things get really, really weird. If that whole wave phase is basically a timeless calculation, what on earth does that do to our neat little ideas of past and future? This one idea might just crack one of the biggest mysteries in all of quantum physics, the delayed choice experiment. The one where a measurement you make now seems to impossibly change what a particle did in the past. Well, what if the secret is that the past was never actually fixed? What if the calculation was still running the whole time? See, during that wave phase, that calculation phase, the system doesn't see time like we do. There's no before and after. For the particle, the entire experiment from the slits at the beginning to the detector at the end is just one single, timeless problem that it has to solve. So it looks at its connection, its omega, to every piece of the puzzle at once. So who wins? It's simple. Whatever part of the setup has the strongest omega value wins. It doesn't matter if we call it the past or the future. If you set up a detector at the end of the experiment that has a super high omega, its influence is going to dominate the whole calculation. It's not that the future is changing the past, it's that the whole thing is one big calculation and the strongest connection always wins out. All right, so let's get down to it. If this framework is legit, it can't just be a neat way to explain old mysteries. It has to make new, solid, testable predictions. And that's exactly what it does. This isn't just another theory. You should think of it as a dare, a direct challenge thrown down to physicists everywhere. Go ahead, prove it right or prove it wrong. And these aren't just, philosophical hypotheticals. These are direct challenges for the lab. Can we steer particles with asymmetric coherence? Can we change an outcome by tweaking a future detector? The theory predicts that in every single one of these cases, the answer is a definitive yes. It's daring us to build these experiments, to prove that we can take control by engineering this omega landscape. The blueprint is right there. The dare has been made. And just imagine for a second, what if these predictions hold up? What if we can really grab that control knob and start turning it? The implications, they're not just big, they're staggering. We'd go from being just passive observers of this weird quantum reality to being its active programmers. I mean, really think about what that means. We could start steering quantum computers toward the answers we want instead of just sifting through probabilities. We could literally guide chemical reactions to create specific molecules we need. We might even finally understand how nature itself is already using this stuff in processes like photosynthesis. This would be a game changer for, pretty much all of science. So that leaves us with one last kind of mind-blowing thought. For 100 years, we've been scratching our heads, puzzled by the quantum world. But what if we've just been handed the keys, a potential control knob for reality itself? The only question left isn't if we can use it, but what should we aim for? What do we want to create?